Hello and welcome to the Deep Space Relax channel. Tonight, we're going to drift into the unknown, toward questions that science has yet to resolve. For all the discoveries humanity has made, the universe remains filled with puzzles, paradoxes, and quiet mysteries that no one can fully explain. Some of them are cosmic, stretching across galaxies and black holes. Others exist here on Earth, in the oceans, the atmosphere, and even within our own bodies. These unanswered questions remind us that science is not a finished book of absolute truths, but an ongoing story still being written. Every mystery opens a doorway to wonder, reminding us that we are explorers in a universe far greater than we can yet comprehend. If you enjoyed drifting off among scientific wonders, feel free to like and subscribe, or simply share your thoughts in the comments below. It helps others find their way here as well. But for now, let these questions carry you. And if you're ready, let's begin. We still don't know why the universe exists at all. It feels like the most basic question imaginable. Why is there something rather than nothing? And yet, science offers no final answer. Physics can describe how the universe behaves once it exists. Cosmology can trace events back to the Big Bang. But why a universe exists in the first place, and why there are laws that allow it to exist, remains unsolved. Quantum physics suggests that what we call nothing is not truly empty. Even the vacuum of space teems with activity, fleeting particles that flicker into existence before vanishing again. Some physicists propose that the universe itself may have emerged in a similar way, that absolute nothingness is unstable and something must inevitably arise. Others argue that our universe may be only one of countless universes within a vast multiverse, each appearing with its own laws. But if that is the case, we are simply pushed back to a deeper question. Why should the multiverse itself exist? Philosophers sometimes suggest that existence is the natural state, and that non-existence is impossible. Perhaps reality, in some form, must always be. But these ideas cannot be tested. No telescope and no particle collider can measure why there is being instead of nothing. Every other question in science rests upon this one. Every star in the sky, every atom in your body, every law of nature exists on a foundation we cannot explain. The fact that reality exists at all remains the deepest mystery we face. The spark that set the cosmos in motion also remains unknown. We can trace the universe's story back nearly 14 billion years, to a time when it was a hot, dense fireball. We call this beginning the Big Bang. But what actually caused it? That question has no answer yet. Cosmologists have reconstructed a detailed history from the moment the universe was only fractions of a second old. In that first instant, a rapid expansion known as inflation may have blown space itself wide open. But what triggered inflation? Why did it begin? And why did it end? These questions remain unanswered. Some theories imagine the Big Bang as a quantum fluctuation, a tremor in the fabric of reality that gave rise to space and time themselves. Others suggest that the Big Bang was not the first event, but only one moment in a cycle of cosmic births and deaths, with universes expanding, collapsing, and beginning again. What complicates the question further is time itself. If the universe includes the birth of time, then asking what came before may not even make sense. Our instruments, the Hubble Space Telescope, the Planck satellite, and the new James Webb, give us snapshots of the infant universe. But none can peer into the very first instant. We know the universe began. We can measure its age, chart its expansion, and study its afterglow. But the spark that set the cosmos in motion, the true first cause, remains hidden in the dark. Time always moves forward, yet no one can fully explain why. With every passing moment, the present slips into the past. We remember yesterday, but not tomorrow. A shattered glass never jumps back together. Heat flows from hot coffee into the surrounding air, but never the other way around. In our experience, time moves in only one direction. This is known as the arrow of time. What makes this so strange is that the fundamental laws of physics do not demand it. At the smaller scales, particles can move forward or backward in time with equal consistency. The equations themselves are symmetrical. Nothing within them requires time to progress in only one direction. And yet, our entire world depends on this one-way flow. Scientists often link the arrow of time to entropy, the tendency for disorder to increase. The universe began in an extraordinarily ordered state and has been slowly running down ever since. But why did it start that way? Why should the cosmos have begun in such a low entropy condition that time could even have a direction at all? Some physicists believe the arrow of time may emerge from the way information spreads. Others suggest it is connected to the expansion of the universe itself. Still, none of these explanations are complete. Time's direction is something we live within every second of our lives, and yet why it flows forward, and only forward, remains one of the most haunting mysteries in science. Most of the universe is made of something we cannot see. When astronomers measure how galaxies rotate, they encounter a puzzle. Stars near the edges move far too quickly, as if held in place by an unseen force. By all known logic, those stars should drift off into space. Instead, they remain bound. The conclusion is unavoidable. Most of the mass in the universe is invisible. We call it dark matter. Dark matter neither shines nor absorbs light. Telescopes cannot detect it directly, yet we know it must exist because its gravity shapes everything around it. It holds galaxies together, bends the paths of starlight from distant clusters, and leaves subtle ripples in the structure of the cosmic web. So what is it? Scientists have searched for decades. Some think it is made of undiscovered particles, perhaps WIMPs, weakly interacting massive particles. Others suggest axions, ghost-like particles that barely interact with ordinary matter. There are even ideas that dark matter could consist of black holes formed in the universe's earliest moments after the Big Bang. Despite enormous effort, the answer remains elusive. Experiments buried deep underground wait for a passing dark matter particle to collide with a single atom. So far, none have. For now, this hidden mass, about 5 times more abundant than ordinary matter, remains one of the universe's greatest unsolved mysteries. An invisible force is also stretching space apart faster and faster. In the 1990s, astronomers studying distant supernovae expected to find that the universe's expansion was slowing down. After all, gravity should be pulling galaxies back together. Instead, they discovered the opposite. The universe is not merely expanding, it is accelerating. This means that some unknown form of energy is embedded in space itself, pushing galaxies away from one another at ever-increasing speeds. We call it dark energy, though the name is only a label for what we do not understand. Dark energy makes up nearly 70% of the entire cosmos, yet we have no clear idea what it truly is. One possibility is that it is a property of the vacuum, a constant energy present even in empty space. Another is that it points toward new physics, perhaps a dynamic field that changes over time. Some theories even suggest it may indicate that our understanding of gravity itself is incomplete. What makes this mystery even more unsettling is its consequence. The ultimate fate of the universe depends on this unseen force. If dark energy remains constant, galaxies will drift farther and farther apart until only vast emptiness remains. If it grows stronger, it could eventually tear apart galaxies, stars, and even atoms themselves. We can measure its influence, but its true nature remains hidden. Dark energy is the invisible hand shaping the long-term future of the cosmos. The laws of physics appear finely tuned for life in ways we do not yet understand. The universe seems balanced on a razor's edge. If gravity were slightly stronger, stars would collapse too quickly. If it were weaker, galaxies might never form at all. If the electromagnetic force differed by even a small fraction, atoms would fail to bind together. The tiniest changes in the constants of nature could erase the possibility of life entirely. This puzzle is known as the fine-tuning problem. Why do the laws of nature have exactly the values they do? There is no obvious reason for gravity, electromagnetism, or the nuclear forces to take the strengths we observe. And yet, if they were even slightly different, our universe would be sterile and empty. Some argue this balance is pure coincidence. Others suggest that countless universes may exist, each with different laws, and we simply inhabit the rare one where life can arise, a kind of cosmic lottery. Another possibility is that a deeper principle, still undiscovered, forces the laws of physics to take these precise values. For now, we cannot say. But when we look at stars, planets, and the fact that we can even ask this question, we are reminded that the universe feels improbably, almost uncannily suited for life. Why this is so remains one of the greatest mysteries science faces. No one knows whether the universe goes on forever or ends somewhere. The observable universe is enormous, about 90 billion light-years across, yet we cannot see beyond it. Light has only had so much time to travel since the Big Bang, creating a horizon we cannot look past. What lies beyond that boundary remains unknown. One possibility is that the universe is infinite, stretching endlessly in all directions with no edge at all. If so, space could contain an unlimited number of galaxies, stars, and perhaps even worlds like Earth. Another possibility is that the universe is finite but unbounded, similar to the surface of a sphere. In such a cosmos, traveling far enough in one direction could eventually bring you back to your starting point. Scientists search for clues in the cosmic microwave background, the faint afterglow left by the Big Bang. Subtle patterns within it may reveal the universe's shape. So far, evidence suggests the universe is very nearly flat, but this alone does not tell us whether it is infinite. For now, we do not know whether the cosmos stretches on forever or loops back on itself. The true size and shape of the universe remain just beyond our reach. Beyond the horizon of what we can observe, there may be endless unknowns. When we look into space, we are also looking into the past. The most distant galaxies send us light that has traveled for more than 13 billion years. Beyond that lies a region forever hidden, the unobservable universe. This boundary is not a physical wall, but a limit set by the age of the universe and the speed of light. Reality continues beyond it, but we can never directly know what exists there. Perhaps it is much the same, with galaxies, stars, and planets extending far beyond our sight. Or perhaps it is radically different. with regions governed by unfamiliar conditions, or even entirely different physical laws. Some theories of inflation suggest that our observable universe is only one bubble within a much larger reality. If this is true, then most of existence lies forever beyond what we can measure. We are confined to a cosmic island. The sky we see is only a small fraction of what may exist, while the rest remains silent, unreachable, and unknown. Some scientists believe that other universes exist, though we cannot prove it. The idea of the multiverse is one of the boldest concepts in modern science. It suggests that our universe may not be unique, but one among countless others. Each universe could follow different laws of physics, possess different histories, or even contain different numbers of dimensions. The idea emerges naturally from certain theories. Inflation may generate bubble universes, each branching off with its own conditions. String theory also predicts a vast landscape of possible realities. In these scenarios, our universe is simply one result among many others. This could even offer an explanation for fine-tuning. We exist in a universe compatible with life, because only in such universes can observers arise. But there is a serious problem. If other universes exist beyond our cosmic horizon, we may never be able to observe them. No light or signal could ever cross that boundary. This makes the multiverse both captivating and controversial. It stretches the definition of science itself, because an idea that cannot be tested may remain forever speculative. Still, the possibility that reality extends far beyond our universe, perhaps infinitely beyond it, remains one of the most fascinating mysteries in physics. Space and time may be woven from deeper rules we have yet to uncover. Einstein's general relativity shows that space and time are not rigid backgrounds, but flexible and dynamic. They bend, curve, and stretch, shaping planetary motion and guiding the flow of light. But at the deepest level, what is this fabric actually made of? At the smallest scales, relativity and quantum mechanics collide. In relativity, space and time appear smooth and continuous. Quantum theory, however, suggests everything should be granular, fluctuating, and uncertain. Reconciling these two views remains one of science's greatest challenges. Some theories suggest that space and time are not fundamental at all. Instead, they may emerge from something deeper, perhaps networks of quantum information or patterns of entanglement that give rise to geometry itself. In this view, space-time is like a surface, beneath which lies a more basic reality we cannot yet access. Others question whether time itself is real, or whether it is an illusion produced by deeper processes. If so, our most basic intuition about reality would be wrong. Space and time feel like the stage on which the universe unfolds, yet the stage itself may not be what it seems. What they truly are remains one of the most profound, unanswered questions in science. A single particle can exist in two places at once, and we still do not know how. Quantum mechanics tells us that particles do not have definite positions until they are measured. Instead, they exist in a superposition, a cloud of probabilities where many outcomes coexist. An electron can be here and there at the same time, passing through both slits of an experiment simultaneously, interfering with itself like a wave. Only when observed does the particle appear to choose a position. This is not merely theory. Experiments have demonstrated superposition, not only in electrons, but in molecules thousands of times larger. Physicists can even create fragile states where objects occupy overlapping possibilities. And yet, no one truly understands what this means. Does the particle physically exist in two places at once? Or does superposition reflect only our incomplete knowledge? Some interpretations suggest reality splits into multiple outcomes. Others claim reality remains undefined until measured. Either way, the ability of a single particle to seemingly exist in two places remains one of the most unsettling mysteries of modern science. Entangled particles echo each other across vast distances, defying explanation. When two particles become entangled, their properties link in ways that ignore separation. Measure one, and the state of the other is instantly known, no matter how far apart they are. Einstein famously called this spooky action at a distance, because it appeared to violate the cosmic speed limit. Nothing should travel faster than light. Yet experiments confirm entanglement is real. Photons, electrons, and even small groups of atoms have been entangled and separated by kilometers. No signal seems to pass between them, yet the correlations remain perfect. It is as if nature keeps a hidden record, ensuring the outcomes stay synchronized. What does this mean? Some physicists suggest reality itself is non-local, woven together more deeply than space and time allow us to perceive. Others propose hidden variables not yet discovered. Still others believe information itself may be the foundation of reality. We already use entanglement in quantum computing and secure communication, yet we still do not know why it works. The universe whispers across distance, and the explanation remains elusive. No one knows why observing something appears to change what it is. One of physics' strangest discoveries is that measurement affects the system being measured. In the famous double-slit experiment, particles behave like waves when unobserved, forming interference patterns. But when we measure which slit a particle passes through, the wave behavior disappears. The outcome changes simply because it was observed. Why this happens remains unknown. One explanation suggests the wave function collapses into a single outcome upon observation. But what qualifies as an observer? Is it a measuring device, a human mind, or something else entirely? Some interpretations argue every possibility occurs, branching into multiple realities. Others suggest particles become definite only when information becomes irreversible. None of these ideas are proven. What we do know is that the boundary between observer and observed is far more complex than once believed. The universe appears to care whether it is being watched, and no one knows why. Gravity is far weaker than every other force, and we still do not know why. Gravity governs the cosmos. It holds planets in orbit, shapes galaxies, and directs the motion of stars. Yet compared to other fundamental forces, it is astonishingly weak. A small refrigerator magnet can overcome the gravitational pull of the entire Earth. Why this is so remains a puzzle. The electromagnetic force, along with the strong and weak nuclear forces, operates on tiny scales with immense strength. Gravity, by contrast, is feeble. Physicists have struggled for decades to explain this hierarchy. One possibility is that gravity spreads into hidden dimensions we cannot see, diluting its strength. Another is that gravity is intrinsically strong, but masked by unknown physics at small distances. Despite centuries of investigation, the weakness of gravity remains unexplained. This imbalance is not trivial. It is essential to the structure of the universe. Without it, stars and galaxies could not exist. Gravity's weakness is the quiet mystery that makes the cosmos possible. Einstein's universe and the quantum world both work, yet refuse to fit together. General relativity describes the large-scale universe with extraordinary precision. Quantum mechanics explains the microscopic realm with remarkable accuracy. Both theories have been tested relentlessly and continue to succeed. Yet they are incompatible. When we attempt to describe situations where quantum effects and gravity coexist, such as inside black holes or at the birth of the universe, the equations collapse. Infinities multiply without limit. The two frameworks cannot be reconciled mathematically. For decades, physicists have searched for a theory of everything to unite them. Ideas like string theory and loop quantum gravity offer promising hints, but none have been experimentally confirmed. Without a unifying theory, we cannot fully understand the universe's origin or the true nature of space-time. The fact that our two most successful theories describe incompatible realities remains one of science's deepest paradoxes. Both work perfectly, yet together they fail. The true heart of a black hole remains unknowable. Black holes are regions where gravity becomes so intense that nothing, not even light, can escape. As matter falls inward, it is crushed toward the center. According to Einstein's equations, everything collapses into a single point of infinite density known as a singularity, but infinity often signals a breakdown in our mathematics. What truly exists at a black hole's core? Some believe the singularity is real, a place where known physics ceases to apply. Others argue that a deeper theory, perhaps quantum gravity, will replace the singularity with something else, a loop of spacetime, a finite core, or an entirely new structure hidden from view. The event horizon seals the interior completely from observation. For now, the center of a black hole remains beyond reach and beyond certainty. It stands as one of the most inaccessible mysteries in all of science. We still do not understand what singularities truly are. A singularity is a point where equations predict infinities. Density without limit, curvature without bound, space and time collapsing into something beyond definition. Black holes contain them. The Big Bang may have begun with one, but what are they really? Are singularities genuine features of nature, or do they signal that our theories are incomplete? Many physicists believe they mark the limits of Einstein's relativity. Somewhere beyond those limits, a new theory that unites relativity with quantum mechanics must take over. Within such a framework, the infinities could dissolve into something finite and describable. Until then, singularities remain puzzles at the boundary of physics. They are places where understanding halts and models fail. What exists beyond them is concealed, waiting for a deeper theory of reality. Whether information disappears inside a black hole remains an open question. When matter falls into a black hole, it appears to vanish forever. But in physics, information, the detailed description of a system's state, is expected to be preserved. So what happens to the information trapped inside a black hole? Stephen Hawking showed that black holes can slowly evaporate through radiation. But if they disappear completely, where does the information go? If it is destroyed, quantum mechanics would be violated. If it escapes, then the information must somehow leak out through Hawking radiation, a process no one fully understands. This dilemma, known as the black hole information paradox, has challenged physicists for decades. Some propose that the information is stored on the event horizon itself, Others suggest black holes may connect to other regions of space-time, allowing information to escape elsewhere. Still others believe our understanding of quantum mechanics may need revision. The fate of information in a black hole is one of the most important unanswered questions in physics. It touches not only black holes, but the deepest foundations of reality itself. Hawking radiation is predicted, yet no one has ever observed it. In the 1970s, Stephen Hawking made a remarkable prediction. Black holes are not entirely black. Quantum effects near the event horizon should cause them to emit faint radiation, slowly losing mass over unimaginable timescales. Eventually, they could evaporate completely. This radiation, now called Hawking radiation, is among the most famous predictions in modern physics, yet it has never been directly detected. Real black holes are surrounded by hot gas and violent environments that overwhelm the faint signal. Detecting it may be impossible with current technology. Still, the implications are profound. Hawking radiation links quantum theory, relativity, and thermodynamics. It suggests black holes possess temperature, and that space-time itself is more dynamic than once believed. Laboratory experiments have attempted to create analogues of Hawking radiation using sound waves and fluids, but these remain indirect hints. Whether Hawking radiation truly exists remains unconfirmed. If it does, it will reshape our understanding of black holes. If it does not, something even stranger may be occurring at the edge of space-time. Black holes may even be gateways to other worlds we do not yet understand. They push physics to its extremes. Inside them, space and time bend in ways we cannot fully describe. Some solutions to Einstein's equations suggest that black holes could connect to other regions of space-time through tunnels known as wormholes. In theory, entering a black hole might lead somewhere else, but this remains speculation. Wormholes, if real, may be unstable. The intense gravity could destroy anything attempting to pass through. Yet mathematically, the possibility remains open. Some physicists suggest that the singularity at a black hole's center could represent a bridge to a new universe with its own space and time. Others propose that black holes might recycle information, helping seed the birth of new cosmic regions. For now, these ideas cannot be tested. No signal can escape a black hole's interior, and so its secrets remain hidden. Still, the idea that black holes are more than cosmic graves, that they could be gateways to something beyond, remains one of the most tantalizing mysteries of all. We still cannot fully explain how the very first stars formed. When the universe was young, it was a dark and simple place. There were no galaxies, no planets, no metals or complex chemistry. Only clouds of hydrogen and helium drifted through the expanding cosmos. At some point, these clouds collapsed, forming the first stars and ending the cosmic dark ages. But exactly how this occurred remains unknown. These first stars, known as population 3 stars, would have been enormous, hundreds of times more massive than our sun. They burned hot and bright, but lived only a few million years before exploding as powerful supernovae. They seeded the universe with the first heavy elements, paving the way for later generations of stars and, eventually, life. The challenge is that we have never observed one directly. No population 3 star has ever been seen. They lived briefly and died long ago, leaving no direct evidence. Astronomers search for indirect clues in the chemical signatures of ancient stars, hoping to uncover traces of their violent origins. The James Webb Space Telescope may finally glimpse their light. Until then, the process that ignited the first stars remains a major unanswered question in astronomy. Some galaxies formed supermassive black holes far too quickly. At the center of nearly every galaxy lies a supermassive black hole, millions or even billions of times the mass of our Sun. We understand how black holes grow by consuming gas, stars, and even other black holes. But in the early universe, we observed black holes that became enormous far too fast. Some already existed less than 1 billion years after the Big Bang. According to existing models, there was not enough time for them to grow through ordinary means. This raises a puzzle. Did they form from the collapse of massive primordial clouds, bypassing smaller stages entirely? Did they originate from the deaths of unusually massive first-generation stars that collapsed into unexpectedly large black holes? Or is there an unknown mechanism that allowed them to feed and expand at astonishing rates? These ancient black holes challenge our understanding of galaxy formation. Solving this mystery could reveal how galaxies themselves came into existence. For now, they remain cosmic enigmas, giants that should not have appeared so soon after the universe began. No one knows why so many galaxies develop spiral shapes. When we picture galaxies, we often imagine graceful spirals, sweeping arms of stars curling outward like cosmic pinwheels. The Milky Way is one of them. But why do galaxies form such intricate spiral patterns? The answer remains uncertain. One idea proposes that spiral arms are density waves, similar to traffic jams on a highway. Stars move through them, clustering temporarily and creating the appearance of permanent arms. Another theory suggests that spirals arise from gravitational interactions, galaxies tugging on one another and stirring stars into curved structures. Computer simulations can recreate spiral patterns, but not with complete consistency. Spirals are common throughout the universe, yet their exact origin and long-term stability remain unresolved. Why some galaxies become elegant spirals while others turn into elliptical shapes is still an open question in astrophysics. When we gaze at the night sky and see the Milky Way stretched across it, we are looking from within one of these mysteries. Our home galaxy's graceful arms are both familiar and unexplained. Fast radio bursts flash across the cosmos, and their cause remains unknown. In 2007, astronomers detected a powerful radio signal lasting only milliseconds. Since then, hundreds more have been discovered scattered across the sky. These signals are known as fast radio bursts, or FRBS. Each one releases as much energy as the Sun emits in an entire year, compressed into a fraction of a second. What produces them remains unclear. Some FRBs repeat, suggesting ongoing sources such as magnetars, highly magnetized neutron stars capable of releasing enormous energy. Others appear only once, hinting at catastrophic events like stellar collapse or the merger of compact objects. But no single explanation accounts for all of them. Fast radio bursts travel across billions of light years, distorted and stretched by the matter that lies between galaxies. They may even allow us to map how matter is distributed throughout the universe. Yet until their true source is identified, they remain cosmic riddles. From time to time, the universe sends a brief, powerful cry across the void. We can detect it, we can measure it, but we still do not know who or what is speaking. Pulsars shine with such perfect regularity that their precision continues to puzzle scientists. Pulsars are the collapsed remains of massive stars, neutron stars spinning rapidly, and sweeping beams of radiation through space like cosmic lighthouses. Discovered in 1967, their signals were initially so regular that researchers briefly wondered whether they could be messages from intelligent life. Today, we know they are natural objects, but their accuracy remains astonishing. Some pulsars keep time more precisely than our best atomic clocks, rotating hundreds of times per second without missing a beat. How can an object so extreme, a star compressed to the size of a city, maintain such remarkable stability? The explanation lies in their extraordinary density and intense magnetic fields, but the full details are still not completely understood. Pulsars can also experience glitches, sudden changes in their rotation speed that occur without warning. These events may arise from interactions deep inside their superfluid cores, where physics behaves unlike anything we encounter on Earth. Pulsars act as laboratories of extreme conditions, yet they continue to guard their secrets. Their rhythms remain among the most precise and mysterious signals in the universe. Magnetars erupt with unusual bursts of energy that we do not fully understand. A magnetar is a type of neutron star with a magnetic field thousands of times stronger than that of an ordinary neutron star and trillions of times stronger than Earth's. These immense magnetic fields twist and fracture, releasing sudden, violent flashes of radiation. A magnetar can emit more energy in a single second than the sun produces over 100,000 years. We observe them as intense X-ray and gamma-ray flares. What exactly triggers these eruptions remains uncertain. Are the bursts caused by starquakes, shifts in the crust of the neutron star under magnetic strain? Or do they arise from sudden rearrangements of the magnetic field itself, snapping and releasing energy like a cosmic rubber band? Some fast radio bursts have even been linked to magnetars, suggesting they may account for at least part of the FRB mystery. Yet the full explanation is still missing. Magnetars are rare, with only a few dozen known, but their power is immense. They remind us that the universe contains engines of energy we are only beginning to comprehend. Cosmic rays strike Earth with extraordinary power, and their origins remain unknown. Every second, high-energy particles known as cosmic rays rain down from space. Most are protons traveling at nearly the speed of light. Many originate from the sun or from supernova explosions, but some are so energetic, so extreme, that their source remains a mystery. The most powerful cosmic rays carry the energy of a fast-thrown baseball, compressed into a single particle. No known process should be able to accelerate matter to such speeds. They may come from supermassive black holes, from active galaxies, or from exotic phenomena we have yet to understand. When these particles collide with Earth's atmosphere, they create cascades of secondary particles that can be detected on the ground. Observatories such as the Pierre Auger Observatory in Argentina track these showers, attempting to trace their paths back to their origins. But magnetic fields throughout space bend their trajectories, erasing the trail. Cosmic rays arrive constantly, yet their most energetic examples remain unexplained. They hint that somewhere in the universe, nature operates particle accelerators far beyond anything humans have built. Vast cosmic voids stretch across space, and their origins are still unclear. The universe is not evenly filled with matter. Instead, galaxies trace a vast cosmic web of clusters and filaments, separated by enormous empty regions. Some of these voids span hundreds of millions of light years, and contain almost no galaxies at all. Why do they exist? Simulations suggest that gravity pulls matter into filaments, naturally leaving empty regions behind. Yet the largest voids appear bigger than expected, raising questions about how they formed. Do they hint at new physics, perhaps involving the role of dark energy in shaping cosmic structure? Or are they simply rare statistical extremes? Voids influence how light travels across the universe and may even provide clues about the nature of dark energy itself. For now, their true origin remains uncertain. Gazing into a cosmic void is like staring into nothingness on the largest imaginable scale. They are among the loneliest regions in existence, vast expanses with no clear explanation. How the universe will end remains an open question. The universe had a beginning, but will it also have an ending? Scientists consider several possibilities, each depending on the nature of dark energy and the balance of cosmic forces. In one scenario, the universe expands forever, gradually cooling as stars burn out and galaxies fade, leaving only darkness behind. This outcome is known as heat death. In another scenario, expansion eventually reverses, pulling everything back together in a catastrophic big crunch. A third possibility is the Big Rip, in which dark energy grows stronger over time, tearing apart galaxies, stars, planets, and ultimately even atoms. Which future awaits us remains unknown. Observations suggest expansion will continue, but dark energy is still too poorly understood to draw firm conclusions. The universe may persist for trillions of years, or it may meet a far more dramatic fate. For now, the ultimate destiny of stars, galaxies, and life itself remains one of science's greatest unanswered questions. Something triggered cosmic inflation, but no one knows what. In the earliest fraction of a second after the Big Bang, the universe is believed to have expanded faster than the speed of light in a process known as inflation. This theory explains why the cosmos appears so smooth and uniform, and why tiny fluctuations eventually grew into galaxies. But what caused inflation remains unknown. Some theories propose a powerful energy field, the inflaton, that briefly dominated the universe before fading away. Others suggest inflation is tied to the quantum structure of space-time itself. We observe inflation's fingerprints in the cosmic microwave background, where patterns match its predictions. Yet the true cause of inflation, and whether it occurred exactly as described, is still debated. Something drove the universe to expand at an unimaginable rate, creating the stage for everything that followed. But the spark behind this expansion remains hidden, an unseen chapter in the story of creation. The origin of life on Earth is still unknown. Life began more than 3.5 billion years ago, yet the details of its emergence remain concealed. Fossil evidence shows microorganisms thriving not long after the planet cooled. But how did non-living chemistry cross the threshold into biology? One hypothesis suggests life began when simple molecules self-organized into chains capable of storing information, perhaps RNA before DNA. Another proposes that life emerged in the energy-rich environment of hydrothermal vents on the ocean floor, where heat, minerals, and chemistry combined. Others suggest that life's building blocks arrived from space, carried by comets or meteorites that struck the young Earth. Each idea has supporting evidence, yet none have been proven. Scientists have succeeded in creating amino acids and other basic molecules under laboratory conditions, meant to mimic early Earth. But assembling a fully living system remains beyond reach. Life's origin may have been a rare event, or it may arise naturally, wherever conditions are right. Until stronger evidence appears, the moment when chemistry first awakened into biology remains one of science's deepest mysteries. We still do not know whether life began in the ocean or on land. Earth offered many possible cradles for its earliest life. The ocean, covering much of the planet, seems like an obvious candidate. Hydrothermal vents, where hot, mineral-rich water pours from the seafloor, provide constant energy and complex chemistry. Many scientists believe life may have started there, with molecules assembling inside natural mineral compartments. Yet another possibility exists. Some researchers argue that shallow pools on land, subject to cycles of drying and refilling, could have concentrated molecules and driven the chemical reactions needed to form life's building blocks. Ultraviolet sunlight, though often destructive, may have powered crucial steps in these processes. Both environments appear plausible. Each offers advantages and each presents challenges. The ocean dilutes molecules, making interaction more difficult, while land-based pools may have been too unstable. Until stronger evidence appears, we still do not know whether life first emerged in the deep oceans or in the shallow waters on land. The answer is buried in the distant past, locked within rocks and fossils that have long since changed. No one knows how the very first living cells came into being. Life is defined not only by chemistry, but by organization. Modern cells are extraordinarily complex, with membranes that separate them from their surroundings and molecular machinery performing countless reactions. But how did the first cell arise from lifeless chemistry? One possibility is that fatty molecules naturally present on early Earth formed tiny bubbles that trapped useful chemistry inside. These primitive membranes may have allowed energy and molecules to pass through while shielding fragile chains of RNA or proteins. Over time, the chemistry contained within could have grown more complex, eventually becoming self-sustaining. Experiments show that simple membranes can indeed form spontaneously under the right conditions. Yet how the transition from these basic compartments to the complexity of a living cell occurred remains unknown. This shift from disordered chemistry to the first organized cell is one of the great mysteries of biology. Until it is understood, we cannot truly explain how life began. DNA adopted a very specific structure, but why it did so remains a mystery. All life on Earth relies on the same molecule to store information, DNA. Its elegant double helix is universal, carrying instructions for every organism. But why this molecule, and why this particular shape? Chemistry allows for many possible ways to store information. RNA, for example, is simpler and may have come first. Yet at some point in life's early history, DNA took over as the primary code. Its stability, reliable replication, and ability to store vast amounts of information made it uniquely effective. Still, we do not know why DNA's precise structure, a double helix with specifically paired bases, became the solution upon which all life depends. Was it inevitable, dictated by chemistry itself? Or was it an accident, one successful outcome among countless failed alternatives? The universality of DNA suggests it may be the best solution nature found. Even so, why life followed this exact path remains an open question, pointing to deeper mysteries within the chemistry that underlies existence. The origins of viruses are still unclear. Viruses are unusual entities. They are not alive in the traditional sense. They cannot reproduce on their own, instead hijacking the machinery of living cells. Yet they are not merely inert matter. They evolve, adapt, and influence the course of life on Earth. Where did they come from? Some scientists believe viruses are remnants of an ancient RNA world, survivors from before fully living cells evolved. Others think they began as fragments of genetic material that escaped from cells and learned to replicate independently. A third possibility is that viruses were once living organisms that became stripped down to their simplest form. The truth may be that viruses emerged in more than one way, their origins as diverse as life itself. What is clear is that they are ancient and may have played a critical role in the evolution of complex life by transferring genes between organisms. Viruses blur the boundary between life and non-life, and their beginnings remain one of biology's most enduring mysteries. Some molecules became alive, while countless others did not, and we do not know why. Early Earth was a vast chemical playground. Simple molecules formed everywhere, from deep-sea vents to volcanic pools to lightning-charged atmospheres. Among them, some linked into more complex chains, such as amino acids and nucleotides. But only a tiny fraction of this chemistry crossed the threshold into life. Why those molecules and not others? What special quality allowed some to organize into self-replicating systems? Was life inevitable once the right ingredients were present? Or was it a rare accident shaped by chance events? Experiments show that many building blocks of life can form under natural conditions, yet creating a self-sustaining, evolving system remains elusive. The leap from chemistry to biology is immense, and we still do not know how it happened. This uncertainty leads to profound implications. If life is inevitable, the universe may be filled with living worlds. If it was a fluke, we may be utterly alone. Why some molecules became alive while others remained inert is one of the most important unanswered questions in science. We still do not know whether life exists anywhere else in the universe. Earth is the only place we know where life exists. Yet with billions of stars in our galaxy and billions of galaxies beyond, it seems unlikely that we are alone. Still, despite decades of searching, no clear evidence of extraterrestrial life has been found. Thousands of exoplanets have been discovered, many within habitable zones where liquid water could exist. Organic molecules are common in space, found on comets, in interstellar clouds, and on distant moons. Mars shows signs of a wetter past. Europa and Enceladus hide oceans beneath icy shells. Conditions for life appear widespread, and yet silence remains. We have not detected signals, discovered microbes on Mars, or found alien fossils. Life may be common but difficult to detect, or it may be extremely rare, requiring conditions we do not yet understand. Until even the simplest alien microbe is found, the question of life beyond Earth remains unanswered. Could life arise from a chemistry entirely unlike our own? We do not know. All life on Earth shares the same foundation: carbon, water, DNA, and proteins. But must life always follow this blueprint? Some scientists suggest silicon, abundant and capable of forming long chains, could serve as the basis for alien life. Others imagine organisms using ammonia instead of water, or exotic biochemistries thriving in methane seas like those on Saturn's moon Titan. Still others wonder whether plasma, magnetic fields, or even information itself could host something resembling life. We do not yet know the answer. All our definitions of life are shaped by a single example: Earth. It may be that carbon and water are the only workable solution, or it may be that the universe contains living systems far stranger than we can imagine. If we discover alien life, it may look nothing like us and challenge our very understanding of what it means to be alive. How common truly habitable worlds are remains uncertain. Astronomers have identified thousands of planets orbiting other stars. Many are small and rocky, some located within habitable zones where liquid water might exist. But how many are genuinely habitable is still unknown. Habitability depends on more than distance from a star. Planets need suitable atmospheres, magnetic protection, and long-term stability. Some may be scorched by radiation, others frozen. Moons may also host life beneath icy crusts, but we cannot yet examine them directly. The galaxy may be rich with habitable worlds, or they may be rare gems. At present, we cannot say. Each new discovery brings us closer, but the true frequency of Earth-like conditions remains one of astronomy's great open questions. We still cannot answer the oldest question of all: are we alone? For as long as humanity has gazed at the stars, we have wondered whether life exists beyond Earth. Despite the vastness of the universe, the abundance of planets, and the widespread chemistry of life, we still have no answer. We listen for signals with radio telescopes. We send probes to planets and moons. We analyze distant atmospheres for signs of life. Yet so far, the silence is complete. Life may be common, while intelligent civilizations are rare or short-lived, or life itself may be rare at every stage, making us a singular accident, or life may be everywhere, hidden from us by distance or difference. The question remains open. Are we a lonely spark in a vast, empty universe, or one voice in a cosmic chorus we have not yet heard? Until evidence appears, the answer to this oldest question remains unknown. Consciousness arises from the brain, yet we do not know how. Every thought, memory, and moment of awareness seems to emerge from neural activity. Scientists can measure electrical signals passing between neurons. They can shut awareness down with anesthesia. They can track brain activity when you focus on an image or a sound. And yet none of this explains why there is subjective experience at all. Why should firing neurons create the feeling of being alive? A brain scan can show activity in the visual cortex when you watch a sunset, but it cannot explain why that moment feels filled with red and gold. It reveals circuits for sound, but not why hearing a favorite song moves you so deeply. Researchers suggest consciousness may arise when information spreads across the brain, when neurons form particular patterns, or even that awareness is a fundamental feature of the universe itself. Yet none of these ideas fully explain the leap from matter to mind. Consciousness is the most familiar thing, what you are experiencing right now. And yet when we try to explain it, it slips through our grasp. We know it comes from the brain, but how remains the deepest mystery of all. Dreams fill our nights, but their purpose is still unknown. Each night as you sleep, your mind creates entire worlds. Some are vivid, populated by familiar people and places. Others are strange and fragmented, fading the moment you wake. These are dreams. And although everyone experiences them, no one truly knows why they occur. Some scientists believe dreams help the brain rehearse experiences, replaying memories to strengthen useful connections. Others think dreams regulate emotion, allowing fear, sadness, or conflict to be processed in a safe, unreal space. Some argue dreams are nothing more than random signals in a sleeping brain, stitched together into a story. What makes dreams even more baffling is how powerful they can feel. A nightmare can jolt you awake in fear, even though you are safe in bed. A pleasant dream can leave you smiling for hours. And sometimes, dreams even solve problems. Writers, artists, and scientists have all described breakthroughs that arrive during sleep. We know the brain remains active while we dream, especially during certain stages of sleep, when the eyes flicker beneath closed lids. Yet the purpose behind it all still escapes us. Dreams are familiar, nightly journeys into strange lands, yet their true meaning stays hidden. Time can feel slow or fast depending on us, and no one fully knows why. Think of a moment when time seemed to crawl, a near accident, a sudden fright, an intense experience. Now think of the opposite, a holiday that felt like it vanished, or hours that disappeared when you were completely absorbed in something you loved. Clock time is steady, but our sense of time is anything but. Why? No one can say for sure. Some believe the brain has an internal clock, and that emotions like fear speed it up, while calmer states slow it down. Others suggest we judge time by how many events the brain processes. A moment packed with new details feels longer. A routine one feels shorter. That could explain why childhood summers seemed endless while adult years slide by. Novelty stretches perception and routine compresses it. But it remains a theory. What we do know is that time in the mind is elastic. It stretches, contracts, and sometimes even seems to pause. The seconds and minutes stay constant, yet our experience of them is mysterious, flowing by rules we still don't understand. We still don't understand how memories are stored and retrieved. Your entire life, your first day of school, your happiest moments, your deepest regrets live somewhere inside your brain. And yet, how those memories are kept and how they return when you need them remains a mystery. Scientists know memories are not like files in a cabinet. They are patterns of activity across many neurons, spread across different regions. The hippocampus helps weave these patterns, acting like an index. But exactly how the brain encodes a memory and later calls it back is not fully understood. Sometimes memories change when we recall them, reshaped before they are stored again. Sometimes we even form false memories that feel completely real. Why do some memories last a lifetime while others fade within days? Why can a certain smell suddenly unlock a vivid childhood scene? Experiments offer glimpses. Neurons that fire when a specific face appears, patterns of activity that match recall. But the full picture is missing. Memory is the glue that makes us who we are. And yet the machinery behind it, how moments become part of us, and how they return years later, remains unknown. Our emotions run deep, but their origins are still mysterious. Emotions shape every part of life. Joy moves us forward. Fear holds us back. Anger flares. Sadness weighs heavy. But where do they come from? Scientists know emotions involve the body as well as the brain. Your heart races when you're afraid. Your stomach tightens when you're anxious. Tears rise when you're sad. Yet the origins of these feelings are still debated. Are emotions hardwired, ancient survival tools built into biology? Or are they constructed by the brain, shaped by culture, memory, and interpretation? We know certain brain regions are involved: the amygdala for fear, the insula for disgust, the prefrontal cortex for regulation. But no single emotion center exists. Music can raise goosebumps. scents can trigger sudden nostalgia. And sometimes we don't even know why we feel what we feel. Emotions are powerful guides, steering choices often more than reason does. Yet how they arise and how they take hold of body and mind remains one of the most intimate mysteries of being human. Creativity arrives in sudden flashes, but we don't know where it comes from. An artist faces a blank canvas, a writer an empty page, a scientist an unsolved problem. Hours can pass with nothing. Then suddenly an idea appears, clear, unexpected, alive. Where did it come from? Creativity feels like a spark, but its source is hidden. Some say it's the brain recombining old ideas in new ways. Others think it requires stepping back, letting the subconscious work while the conscious mind rests. Many breakthroughs in history came not at desks, but in dreams, showers, or quiet walks. Brain scans suggest different networks are involved, some generating ideas, others evaluating them. But that still doesn't explain the moment of inspiration. Why does the solution arise suddenly with such force? Why do some people overflow with ideas while others struggle? Creativity is one of humanity's greatest gifts, shaping art, science, and progress. Yet the place ideas come from, the quiet leap from nothing to something, is a mystery we still cannot explain. Déjà vu makes the present feel repeated, and no one truly knows why. You step into a room you've never visited, and suddenly everything feels strangely familiar. You feel as if you know what will happen next, even though you don't. This is déjà vu, and it remains one of the mind's strangest mysteries. Scientists suggest it may be a memory trick. Perhaps the brain misfires, creating a false signal of familiarity without a real memory behind it. Others think it happens when one part of the brain processes an experience a fraction earlier than another, making the moment feel replayed. Still others believe it comes from similarities between a current scene and a forgotten past one, fooling the mind. What makes déjà vu so uncanny is its intensity. For a few seconds, reality feels doubled, both new and remembered. Almost everyone experiences it, yet no one can predict when or why. Déjà vu reminds us that memory and perception are fragile, and that the brain can sometimes deceive us in ways we don't yet understand. Placebos can heal, but the power behind them is still a mystery. Imagine swallowing a pill, being told it will reduce your pain, and then actually feeling relief, even though the pill contained nothing at all. This is the placebo effect, and it is real. Doctors have seen placebos reduce pain, ease depression, and even calm symptoms of Parkinson's disease. The effect is thought to come from expectation. Believing something will help can trigger real changes in brain and body. Placebos can release natural painkillers, shift brain chemistry, and influence the immune system. What makes the placebo effect so strange is that it can work even when people know they're taking one. Somehow, the ritual of treatment, the pill, the doctor, the belief, taps into hidden healing pathways. But why some people respond strongly to placebos while others do not remains unclear. The placebo effect blurs the boundary between mind and body, showing that belief itself can sometimes heal in ways we still don't fully understand. We don't even know why we need sleep at all. Every night we surrender to sleep. We close our eyes, drift into dreams, and lose awareness for hours. But why do we need it? Sleep is dangerous when you think about it. In the wild, an animal that sleeps is vulnerable, and yet every species does it in some form. That suggests sleep is essential. But essential for what? Some scientists believe sleep helps the brain store memories and learn. Others think it clears waste, cleaning the brain of harmful buildup. Sleep may restore energy, regulate emotion, and strengthen the immune system. It may even help the brain rewire itself, keeping connections balanced. And yet, no single explanation fits all the evidence. Different animals sleep in remarkably different ways. Dolphins sleep with only half their brain at a time. Some birds sleep while flying. Some creatures need very little sleep. What we do know is that without sleep, minds and bodies break down quickly. Why we spend a third of our lives doing it remains one of science's great mysteries. We still don't know why aging happens the way it does. Every living being on Earth ages. Skin wrinkles, hair turns silver, muscles weaken, and eventually the body begins to fail. Yet science still cannot fully explain why aging occurs or why it unfolds so differently across species. One explanation focuses on DNA. Each time a cell divides, the protective caps at the ends of chromosomes, known as telomeres, become shorter. Eventually, the cell can no longer divide at all. Another theory points to damage. Oxygen molecules and other byproducts slowly wear cells down over time, leaving scars that build up. Others view aging as a byproduct of evolution, a trade-off that directs energy toward reproduction in youth while leaving the body more fragile later in life. Nature, however, offers exceptions. Some turtles and fish show almost no visible signs of aging. Certain jellyfish appear able to return to earlier stages of life, effectively bypassing decline. Naked mole rats live far longer than expected and show resistance to many age-related diseases. Why do some creatures avoid aging while humans do not? And why does the process unfold in us with such regularity? The answers remain out of reach. Solving this mystery could transform medicine forever. For now, aging remains a riddle written into our very cells. The limits of human lifespan are still unclear. The longest verified human life ended at 122 years. But was this the true biological ceiling, or simply an extraordinary exception? No one knows for certain. Some researchers argue humans have a hard upper limit. Beyond a certain age, the body can no longer repair itself fast enough to survive. Data shows survival rates drop sharply after 110, suggesting a biological boundary. Others argue there is no strict maximum, only increasing odds of frailty, illness, and chance. What is puzzling is that while average life expectancy has risen dramatically due to medicine, hygiene, and nutrition, maximum lifespan has barely changed. Almost no one lives beyond 115, regardless of era or location. Still, scientists continue searching for ways to extend life. They study families of super-agers who remain healthy into extreme old age. They look for protective genes and test drugs that slow aging in animals. Could humans one day reach 150 years, or even 200? The evidence offers clues, but no certainty. The true upper boundary of human life remains hidden, waiting to be revealed. Some animals can regrow entire limbs, and we still don't understand how. If a salamander loses a leg, it grows a new one. If a starfish loses an arm, it slowly rebuilds it. Some worms can regenerate an entire body from a single fragment. In nature, regeneration is surprisingly common, yet humans cannot do it beyond the smallest scale. A child's fingertip may regrow, but a lost limb never does. Why them and not us? Scientists studying salamanders have found that after injury, nearby cells seem to reset, returning to a flexible, embryo-like state. From there, they form muscles, bones, and nerves in perfect order. Humans share many of the same genes, yet for reasons we don't understand, our bodies do not activate them in the same way. If we could unlock this ability, medicine would be revolutionized. Hearts could heal themselves, spinal cords could regrow, limbs could return. Still, after decades of research, the full blueprint of regeneration remains hidden. Why evolution granted this power to some species and not to us remains a mystery. Certain creatures live far longer than expected, and no one fully knows why. Most animals follow a simple rule. Small bodies live short lives, large ones live longer. Mice live a few years. Elephants live many decades. Humans, with our long lives, are already outliers among primates. But scattered through nature are species that break these rules entirely. The Greenland shark drifts beneath Arctic ice for centuries, with lifespans exceeding 400 years. Bowhead whales sing in frozen seas for over 200 years. Tiny naked mole rats live 10 times longer than similar rodents and resist many signs of aging. Some clams have been found alive after more than 500 years. Why? Scientists have identified clues: unusual proteins that resist damage, efficient DNA repair systems, and extremely slow metabolisms. But no single explanation fits them all. Each species appears to hold its own key to longevity, one humans cannot yet replicate. These animals show that aging is not a fixed law, but a puzzle with many answers. Some animals survive being frozen solid, yet their secrets remain hidden. Imagine being frozen into ice, blood crystallized, heart stopped, body rigid. For most creatures, this means death, but not for all. The wood frog of North America freezes completely during winter. Its heart stops, its body stiffens. When spring arrives, the frog thaws and hops away unharmed. Certain insects and fish do the same. Tardigrades, tiny water bears, survive not only freezing, but even the vacuum of space. How do they manage this? Some species flood their bodies with antifreeze-like molecules that prevent ice crystals from destroying cells. Others use sugars that stabilize tissues during freezing. Yet how delicate organs like the brain and heart survive months without activity remains unclear. If humans could master this ability, it could transform organ transplants, medicine, and even space travel. We might preserve organs for months or place people into hibernation for long journeys. For now, the secret belongs only to these resilient survivors. Whales live for centuries with remarkably little cancer, and no one knows how. The bowhead whale can live over 200 years, swimming through icy Arctic waters. What makes this remarkable is not just its age, but its health. Despite massive size and countless cells, cancer is rare. This contradiction is known as Peto's paradox. Larger animals should, in theory, face higher cancer risk, yet whales and elephants do not. In elephants, scientists have found extra copies of tumor suppressor genes. In whales, the explanation is less clear. Perhaps their DNA repair systems are unusually strong. Perhaps their metabolism limits damage. Perhaps they rely on biological pathways we have yet to discover. Unlocking this mystery could change cancer treatment forever. For now, the whale's secret drifts beneath the waves, unsolved. Birds can sense Earth's magnetic field, but how they do it is still uncertain. Every year, birds migrate across continents. Tiny warblers fly from Europe to Africa. Arctic terns cross oceans, circling the globe. They travel thousands of miles with extraordinary precision. Evidence suggests they use Earth's magnetic field, but the mechanism remains debated. Some studies point to microscopic magnetite crystals acting as internal compasses. Others suggest special proteins in the eyes allow birds to perceive magnetic fields as faint visual patterns. No single theory explains everything. What is clear is the accuracy of their navigation. Even under cloudy skies, birds stay on course. Released in unfamiliar places, they still find their way. It is a sense humans lack, like an invisible layer of reality we cannot access. Monarch butterflies cross continents using a map we cannot read. Each autumn, delicate monarchs begin an impossible journey. They fly thousands of miles from North America to a few mountain forests in central Mexico. There they gather in dense orange swarms. What makes this astonishing is that no single butterfly completes the round trip. The return migration is carried out by later generations, yet each year they reach the same groves. Scientists know monarchs use the sun as a compass and may sense Earth's magnetic field. But how this information is passed across generations remains unknown. Migrating animals cross vast distances, guided by rules we do not fully understand. The natural world is filled with great migrations. Salmon hatch in mountain streams, swim to the ocean, and years later return to the very stream where they were born. Sea turtles crawl from the sea onto the same beaches where their lives began. Birds, whales, and insects all travel across the planet with astonishing precision. Scientists have uncovered clues. Some animals navigate using the stars, the sun, and the tilt of Earth's axis. Others may follow magnetic fields or extremely subtle senses we do not fully perceive. Yet none of these explanations completely accounts for their accuracy. How does a bird return to the same tree year after year? How does a turtle cross an entire ocean to reach a single stretch of sand? These journeys remain partly unexplained, guided by abilities we still do not fully understand. Migration is one of life's oldest rhythms, a vast and mysterious dance written into the instincts of animals. Homing pigeons return home from anywhere, and the mystery endures. For centuries, people have been fascinated by homing pigeons. Release one hundreds of miles from its loft, and it will rise into the air, circle briefly, and then fly straight home. No map, no visible guide, only an unseen sense of direction. Researchers have proposed many explanations. Some think pigeons use the sun as a compass, adjusting for time of day. Others believe they sense Earth's magnetic field, functioning like a built-in GPS. Still others argue pigeons rely on smell, creating a scent map of their home region and following it back. Yet none of these ideas fully explains their accuracy. Even when released in unfamiliar places under cloudy skies, pigeons still find their way home. The answer seems hidden in their biology, a secret compass we have yet to uncover. For pigeons, the world is filled with invisible signals. For us, it remains an unsolved puzzle. No one knows exactly how humans first developed language. Language is what makes us human. Through it, we share ideas, pass down stories, and build civilizations. But its origin remains one of the deepest mysteries of our past. Our closest relatives, chimpanzees and bonobos, communicate with gestures and sounds, yet none approach the complexity of human speech. At some point, our ancestors crossed a threshold, moving from simple calls to structured language with grammar, abstraction, and limitless expression. When and how did this happen? Some theories suggest language began with gestures, with spoken words emerging later. Others propose that rhythmic sounds, chants, and songs slowly evolved into speech. Archaeological evidence shows symbolic carvings and art tens of thousands of years old, suggesting minds already capable of complex communication. But spoken sounds leave no fossils. Language lets us describe what is absent, plan ahead, imagine futures, and dream. It is both a survival tool and a window into thought. Yet the moment when humans first spoke is lost to time. We can only imagine the conversations that started it all. Laughter is universal, but its origins remain uncertain. Wherever humans live, they laugh. The sound crosses cultures, ages, and languages. Babies laugh long before they speak. Groups laugh together, their joy spreading easily. Yet why laughter evolved is still unclear. Some scientists believe laughter began as a signal of safety, showing that a threat had passed and fear could turn to relief. Others trace it to primates at play, whose panting during chasing and wrestling resembles laughter's rhythm. But laughter is more than survival. It reduces stress, bonds groups, and releases chemicals that calm the body. Strangely, we laugh not only at humor, but at relief, awkwardness, and even sorrow. Sometimes, laughter erupts when it seems completely out of place. Why should a simple burst of sound carry such power? We do not know. What we do know is that laughter is ancient, shared by all humans, and deeply mysterious. It is the music of joy woven through our species, its roots hidden in our past. Music moves us profoundly, yet science cannot explain why. A melody can bring tears, a rhythm can quicken the heart, a song can bind us to memories we thought were lost. Music has no obvious survival function, yet it shapes every culture on Earth. Why? Some believe music evolved to bond early communities through song and dance. Others think it began as courtship, a way to signal health and skill. Still others see it as a byproduct of language and memory, a beautiful evolutionary accident. What makes music even more puzzling is its power. Stroke patients who struggle to speak can still sing. People with dementia recall lyrics long after other memories fade. Music can synchronize heartbeats, soothe newborns, and drive armies forward. Why organized sound reaches so deeply into mind and body remains unanswered. Music is one of the most universal and mysterious forces in human life, an invisible thread connecting us all. Love is powerful and complex, and its full nature remains unknown. Love shapes human lives more than almost anything else. It binds parents to children, partners to each other, friends across years. It inspires sacrifice, creativity, and joy. Biology explains parts of it. Love floods the brain with dopamine and oxytocin, chemicals tied to reward and bonding. Evolution suggests it helped keep parents together long enough to raise helpless offspring. But these explanations fall short. Why does love sometimes arrive suddenly and overwhelmingly? Why does it last a lifetime for some and fade for others? Why do people risk everything for it, even against reason? Love is not only chemistry or instinct. It is memory, story, imagination, and something more. We can map its effects in the brain, but not its meaning. Love is universal yet deeply personal, shared by all humans and unique to each. Its full nature remains one of life's greatest mysteries. Humans cry emotional tears, and no one knows why. Tears protect the eyes, washing away dust and salt, but only humans cry in response to emotion. We cry from sadness, joy, frustration, and even laughter. Why? One idea is that tears act as social signals, showing vulnerability and inviting empathy. Another suggests they release stress chemicals, though evidence is mixed. Tears may strengthen social bonds by making feelings visible. What deepens the mystery is that we cry for opposite emotions. Tears fall in grief and in joy, in despair and in relief. No single explanation captures this. Tears remind us that we are emotional beings, not purely rational ones. They make inner experience visible. Why humans alone evolved this response remains unsolved, a secret carried in every tear. Myths appear across cultures in strikingly similar forms, and we do not know why. Across deserts, islands, mountains, and forests, cultures separated by oceans tell stories that echo one another. Flood myths, sky gods, tricksters, underworlds. The patterns repeat. Some believe the human mind naturally generates certain themes from shared experience: fear of death, hope for renewal, awe of the sky. Others suggest myths spread through migration and trade, leaving traces in distant lands. Still others think myths arise from deeper patterns in the brain itself, symbols born from a shared inner landscape. Whatever the cause, myths carry meaning. Cultures find essential. They explain the unknown, bind communities, and pass wisdom through generations. Yet the recurrence of similar stories where contact seems impossible remains unexplained. Humans often cooperate with strangers, and the origins of this instinct are unclear. Humans are unusual among animals. We help not only family and allies, but also strangers. We donate blood, build communities, and risk ourselves for people we may never meet. Why? Evolutionary theories suggest cooperation strengthened groups. Others point to reciprocal altruism, help given in expectation of return. But humans often help without hope of reward. Experiments show even young children choose to help before they fully understand social rules. Something in us is drawn to cooperation. Whether it arose from survival pressures or a deeper moral instinct remains unknown. Helping strangers is one of humanity's most beautiful and mysterious traits. Civilizations rise and fall, yet the forces behind them remain debated. Throughout history, powerful civilizations have grown, flourished, and collapsed. The Maya, the Indus Valley, Mesopotamia, Rome. Some blame climate shifts, drought, or disasters. Others point to war, corruption, or depleted resources. Some believe civilizations follow repeating cycles of growth and collapse. The truth may involve all of these, or something else entirely. What is striking is how sudden collapse can be. Cities are abandoned, knowledge is lost, and generations fade into silence. Civilization is fragile, and the forces that sustain or destroy it are not fully understood. History reminds us that nothing lasts forever, and the reasons why remain uncertain. Human curiosity drives us, but its source is unknown. Why do we wonder? Why do we look at the stars and ask questions no other creature seems to ask? Curiosity defines us, yet its origin is unclear. Some see it as an extension of survival, helping us seek food and safety. Others view it as an evolutionary advantage, pushing exploration and invention. But curiosity often goes beyond survival. It drives us to study distant galaxies, ancient languages, and questions with no practical answers. Children show curiosity from the start, reaching for the unknown and asking endlessly. It seems built into us. But why this hunger to understand exists remains unexplained. Curiosity shapes science, art, and discovery. Yet the spark behind the question why is still a mystery. Storytelling is universal, and no one knows why we need it. Every culture tells stories, around fires, on stages, in books and films. Stories carry heroes, villains, struggle, and triumph. They entertain, teach, and inspire. Some say stories pass knowledge in memorable form. Others believe they bind communities through shared meaning. Some see them as rehearsal, allowing us to imagine choices safely. Yet stories go beyond function. They create worlds that never existed and make us care deeply about imaginary lives. No other species does this. Why humans need stories remains unknown. What we do know is that storytelling is as old as language itself, a thread connecting all cultures. Lightning sometimes forms glowing spheres, and we still don't know how. Most people know lightning as a brief flash followed by thunder. But there is a stranger phenomenon that has puzzled witnesses for centuries. Ball lightning. Instead of a bolt, it appears as a glowing orb drifting silently through the air, sometimes even entering homes. Witnesses describe spheres the size of a grapefruit, glowing white, orange, or blue, lasting several seconds before vanishing or exploding softly. For a long time, ball lightning was dismissed as myth or illusion. Ball lightning has long seemed like a myth, but in recent years, credible reports and a handful of scientific recordings suggest it is real. The problem is that no one knows what it actually is. Some theories describe plasma trapped inside electromagnetic fields. Others imagine vaporized silicon glowing after a strike. Some propose chemical reactions ignited in the air. But no single explanation matches every account. The mystery deepens because ball lightning has been reported indoors, even drifting through windows without breaking them. It seems to defy ordinary physics, behaving like both matter and light. Despite thousands of observations, it remains rare, unpredictable, and unexplained. Ball lightning moves through history as one of nature's strangest and most beautiful riddles, a ghostly flame in the sky. Earthquake lights appear in the sky, and no one knows what causes them. During some powerful earthquakes, witnesses report luminous glows in the air. They take many forms: flickering blue flames near the ground, lightning-like flashes above cities, or strange orbs hovering over fault lines. These earthquake lights have been described for centuries, and modern cameras have captured them too, confirming they are real. What creates them is still unknown. One idea suggests that stressed rocks release electrical charges during quakes, sparking light in the air. Another proposes that tectonic forces ionize gases near the ground, causing them to glow. But not every earthquake produces lights, and the appearances vary widely. Sometimes, the lights are seen before the quake, leading to speculation that they could serve as a warning system. Yet their rarity and unpredictability make them difficult to study. Earthquake lights remain among the eeriest natural mysteries, sudden flashes of otherworldly glow amid chaos, reminders that Earth itself holds secrets written in fire and stone. Some volcanoes erupt with terrifying force, and the triggers remain mysterious. Volcanoes are among the most destructive forces on Earth. Many eruptions are dramatic but manageable: lava flows, ash plumes, smaller explosions. But every so often, a volcano unleashes unimaginable violence, blasting enough material into the sky to shift climate and spread devastation across continents. What makes some eruptions so catastrophic? Scientists know pressure builds as magma rises and gases expand, but the precise tipping point is uncertain. Some volcanoes sleep for centuries and then erupt with little warning. Others rumble and smoke for years yet never explode. The mystery is what flips the balance from silence to disaster. Events like Krakatoa in 1883, Tambora in 1815, and the eruption of Mount Toba 74,000 years ago released energy on a scale comparable to nuclear weapons. Toba may even have nearly wiped out humanity, yet modern science still cannot predict which volcanoes will erupt this way or when. We track tremors, measure gases, and image magma chambers, but the inner mechanics of super eruptions remain hidden. Volcanoes remind us that Earth is alive and capable of mysteries we have not yet learned to master. Why plate tectonics began on Earth is still debated. The surface of our planet is in constant motion. Continents drift, mountains rise, oceans open and close, all driven by shifting tectonic plates. Without plate tectonics, Earth would lack its landscapes, its earthquakes, and its volcanoes. Life itself may depend on this ceaseless churning. But why did it start here and not on other worlds? Mars and Venus show no active tectonics. Their crusts are stagnant, locked in place. Yet billions of years ago, Earth's crust fractured into huge plates that slide and grind endlessly. Did water act like a lubricant, weakening rock and allowing motion? Did internal heat strike a perfect balance between strength and flow? Or did ancient impacts crack the crust and set the system in motion? We do not know. Computer models offer competing answers, but none fully explain why Earth alone developed this feature. Without plate tectonics, the carbon cycle that stabilizes climate might fail, leaving the planet barren. Plate tectonics is what makes Earth dynamic and habitable. Yet why it began and why it seems unique in our solar system remains unsolved. The origin of Earth's water is still uncertain. Water covers most of our world, filling oceans, rivers, and clouds. It is essential for life, yet its source remains a major mystery. Did water arrive on asteroids and comets during the chaos of the early solar system? Some evidence supports this, since many space rocks contain ice. But the chemical signatures of Earth's water do not always match those found in comets. Another idea is that water was here from the beginning, trapped deep in Earth's mantle and slowly released to the surface over vast spans of time. Perhaps both are true. Some water born on Earth, some delivered from space. But the balance is still debated. What we do know is that Earth is unusual. Nearby planets like Venus and Mars are mostly dry, their water lost or locked away. Something about Earth allowed oceans to collect and remain stable. Water feels ordinary, yet its story is strange. Every drop you drink carries the mystery of its beginnings, a riddle reaching back to the birth of our planet. The far side of the moon looks strangely different, and we don't know why. For most of history, humans saw only one face of the moon. The far side remained unknown until spacecraft revealed it in the 20th century, and the images were surprising. The near side, familiar to us, is marked by dark Maria, broad plains of cooled lava. The far side looks nothing like it, rugged, mountainous, with almost no Maria at all. Why should two hemispheres of the same moon differ so dramatically? One idea suggests uneven heating long ago, with Earth's gravity warming one side more intensely. Another proposes that an ancient collision reshaped one hemisphere, but not the other. Some theories focus on internal dynamics, differences in crust thickness, or volcanic history, but no explanation fits perfectly. The moon should be more symmetrical, yet it is not. Its hidden face carries scars and secrets that resist simple answers. Even today, as orbiters circle and landers touch down, the far side keeps its mystery, as if it remains half a stranger to us. Earth's core powers a magnetic field, but the details remain unclear. Deep beneath our feet, more than 3,000 kilometers down, lies Earth's core, molten iron and nickel swirling around a solid inner sphere. Its motion generates the magnetic field that shields us from solar wind and cosmic radiation. Without it, our atmosphere could be stripped away, leaving Earth barren like Mars. Yet despite its importance, we still don't fully understand how it works. We cannot drill to the core, so we rely on indirect clues, seismic waves, magnetic records, and computer models. We know the outer core flows like a liquid, and that this motion drives the geodynamo. But why Earth's field sometimes weakens, wobbles, or reverses is still uncertain. Other planets add to the puzzle. Mars once had a magnetic field, and then lost it. Why did Earth keep its protective shield, while Mars did not? The beating heart of our planet remains hidden from direct study. We see its effects in compasses, auroras, and in the simple fact that we survive, yet its inner workings remain mysterious. Earth's magnetic poles sometimes flip, and the cause is still unknown. Over and over through geological time, the magnetic poles have swapped. North becomes south, and south becomes north. Ancient rocks record these reversals in patterns that stretch back millions of years. The last complete reversal occurred about 780,000 years ago. But why do these flips happen? Scientists suspect turbulence in the liquid outer core. The engine of the magnetic field sometimes becomes unstable, causing the field to weaken and then rebuild in the opposite direction. Yet the precise trigger remains unclear. Some reversals occur quickly, others take thousands of years, and sometimes the field weakens without fully flipping. The mystery deepens when we consider possible consequences. During a reversal, the field weakens, allowing more radiation to reach Earth. Would that disturb ecosystems? Did past reversals shape evolution? We do not know. What we do know is that Earth's magnetic field is not fixed. One day, north will again become south, and the reason remains buried in the depths. Ice ages come and go, and we still don't know what drives them. Over millions of years, Earth's climate has swung between ice ages and warmer intervals. Vast glaciers advanced and retreated, carving landscapes and reshaping continents. But why this cycle happens is still debated. Some explanations point to shifts in Earth's orbit and tilt, known as Milankovitch cycles, which change how sunlight reaches the planet. Others emphasize volcanic eruptions, changing ocean currents, or carbon dioxide feedback loops. Perhaps all of these interact in ways we do not yet fully understand. What is certain is that the pulse of ice and thaw has shaped human history. Our ancestors migrated, adapted, and survived under the shadow of glaciers. Civilizations rose as climates warmed, but the deeper cause, the driving engine behind these repeating freezes, remains unclear. Ice ages remind us that Earth's climate is never truly fixed, but part of a mystery far larger than ourselves. Mass extinctions strike suddenly, and their causes are still unsettled. 5 times in Earth's history, life has nearly been erased. The dinosaurs' extinction 66 million years ago is the most famous. But even greater catastrophes came earlier, like the Great Dying 250 million years ago, when most life on Earth disappeared. Asteroid impacts, supervolcanoes, climate shifts, and changing oceans have all been proposed as causes. Sometimes the evidence points clearly, as with the asteroid that hit at the end of the Cretaceous. Other times it is murky, with multiple disasters overlapping and triggering cascades of collapse. Why some species vanish while others survive is equally mysterious. Why did mammals endure the asteroid strike while dinosaurs perished? Why do some extinctions unfold as slow decline, while others happen in a geological instant? Mass extinctions remind us of life's fragility, but also of its resilience. Each one cleared the stage for new forms of life to rise. But the forces behind them, sudden, devastating, and unpredictable, remain only partly understood. Saturn's rings appear young, and we don't know how they formed. Saturn's rings are among the most breathtaking sights in the solar system. Vast bands of shimmering ice and dust encircling a giant planet. They stretch for hundreds of thousands of kilometers. Yet they are astonishingly thin, sometimes only a few dozen meters deep. For centuries, we assumed they were as old as Saturn itself, more than 4 billion years. But recent evidence suggests otherwise. The rings look strangely clean, made mostly of bright ice with little dust. If they were ancient, they should be darker, dirtied by micrometeorite impacts over eons. Measurements from NASA's Cassini spacecraft hinted that the rings may be only a few 100 million years old, a blink in cosmic time. If true, how did they form so recently? Perhaps a moon drifted too close and was torn apart by Saturn's gravity. Perhaps comets or asteroids shattered, leaving debris that spread into rings. But no explanation is certain. Saturn's rings may be temporary, destined to rain into the planet over the next 100 million years. We are living in the brief era when Saturn wears this dazzling crown. The mystery of their origin remains one of the solar system's most beautiful unsolved puzzles. Uranus spins on its side, and no one knows why. Among the planets, Uranus is an oddball. Instead of spinning upright like Earth, it rolls through space on its side. Its axis is tilted by 98 degrees, leaving it rotating almost horizontally. For part of its orbit, one pole points straight at the Sun, bathing that hemisphere in decades of light, while the other lies in darkness. How did Uranus end up like this? The leading idea is that long ago, a colossal impact with a protoplanet knocked it onto its side. But such a collision should have left behind clues, like a large moon or a visible scar in its atmosphere. Another theory suggests multiple smaller impacts gradually tilted the planet. Still others propose gravitational interactions with giant planets in the early solar system pulled Uranus into its strange posture. Whatever the cause, Uranus remains unique. Its sideways spin creates bizarre seasons and may even influence its magnetic field, which is also oddly tilted and offset. No probe has visited Uranus since Voyager 2 in the 1980s, leaving most of its mysteries unsolved. Until we return, Uranus rolls quietly on its side, carrying a cosmic riddle that no other planet shares. Venus rotates backwards, and its strange past is still debated. Venus, often called Earth's twin, is nearly the same size and mass as our planet, but it is also profoundly strange. One of its strangest traits is its rotation. While most planets spin in the same direction they orbit the Sun, Venus turns the other way. On Venus, the Sun rises in the west and sets in the east. Even stranger, a single Venus day lasts longer than its year. How did this happen? One idea is that Venus was struck by a massive object early in its history, flipping its spin. Another suggests tidal interactions with the Sun slowly reversed its rotation. Still another theory imagines Venus once spun rapidly like Earth, but its thick atmosphere and internal dynamics gradually slowed and reversed it. No theory fully explains the planet we see today. Its atmosphere, dense with carbon dioxide and sulfuric acid, may hold clues, but for now, Venus keeps her secrets. Beneath perpetual clouds, Venus turns slowly backward and against expectation, a reminder that even familiar-looking worlds can hide the strangest histories. Neptune is full of storms we don't fully understand. At the edge of the solar system, Neptune howls with winds faster than any on Earth, reaching nearly 2,000 kilometers per hour. Vast storms swirl across its deep blue atmosphere, appearing and vanishing in ways that baffle scientists. The most famous, the Great Dark Spot, was discovered by Voyager 2 in 1989. It was a storm the size of Earth. But when the Hubble Space Telescope looked a few years later, it had vanished completely. Other dark spots have since appeared, drifting across the planet, sometimes breaking apart or fading without warning. Why does Neptune, so far from the Sun, have such violent weather? Its distance means it receives little solar energy. Some believe Neptune's internal heat drives the storms, while others think atmospheric dynamics amplify tiny changes into massive tempests. But the details remain unclear. Neptune remains a distant storm world visited by only one spacecraft. Its mysterious weather shows us that even in the frozen reaches of the solar system, chaos can reign. Jupiter's Great Red Spot has raged for centuries, and its future is uncertain. For as long as humans have aimed telescopes at Jupiter, the Great Red Spot has churned in its atmosphere, a storm so large it could swallow Earth whole. It has been raging for at least 350 years, perhaps much longer. But why it began and why it has lasted so long remain mysteries. The storm is an anticyclone spinning counterclockwise in Jupiter's southern hemisphere. Fueled by the planet's immense atmosphere, it seems almost timeless. Yet in recent decades, scientists have noticed that it is shrinking. Once wide enough to fit 3 Earths across, it now spans barely more than one. Some predict it may fade away entirely in the coming century. Why did the storm form where it did? Why has it survived for centuries when storms on Earth last only days or weeks? And will it truly vanish or revive itself in cycles we don't yet understand? The Great Red Spot is a cosmic paradox. At once ancient and fragile, it remains one of the most iconic mysteries in the skies. Comets cluster in a distant cloud we've never seen directly. Comets, with their glowing tails, have fascinated humans for millennia. They sweep in from the edges of the solar system, loop around the sun, and then disappear again into darkness. Astronomers believe these icy wanderers come from a vast reservoir far beyond Pluto, the Oort cloud. The Oort cloud is thought to contain trillions of icy bodies, leftovers from the birth of the solar system. It reaches so far that its edge may blend into interstellar space. And yet, despite being the source of comets, it has never been observed directly. The objects are too small, too distant, and too faint. We know this odd cloud only from the comets it sends us, visitors that hint at a vast, unseen population beyond. Was it created by the scattering of early planets? Does it extend farther than we imagine? We don't know. The Oort cloud is the great unseen frontier of our solar system, a ghostly shell surrounding us, filled with secrets we have yet to glimpse. Many moons hide oceans beneath their ice, but we don't know what lives there. Beyond Earth, water is not rare. Moons like Europa, Enceladus, and Titan may hide oceans beneath thick shells of ice. Some of these oceans could be larger than all Earth's seas combined. They remain liquid because the gravitational pull of their planets needs the moon's interiors and generates heat. What makes these oceans so exciting is their potential for life. On Earth, where water exists, life almost always follows. Hydrothermal vents deep in our seas thrive with creatures independent of sunlight. Could similar ecosystems exist beneath alien ice? We have hints. Enceladus sprays plumes of water into space, rich with organic molecules. Europa's cracked surface suggests activity below, but we still can't see into those oceans directly. What strange forms of life might swim there? Simple microbes, or something far more complex? Until we explore these hidden seas, the answer remains locked beneath ice, waiting in the dark. Enceladus sprays water into space, and we don't know what stirs below. Saturn's small moon. Enceladus looks unassuming, just a bright, icy sphere. But when NASA's Cassini spacecraft flew past, it found geysers erupting from fractures near the South Pole, spraying water vapor and ice grains far into space. These plumes contained salts, organics, and signs of chemical reactions that on Earth would hint at habitability. Beneath the surface, Enceladus hides a global ocean warmed by Saturn's tidal pull. The geysers may be vents linking this ocean to the surface. But what drives the eruptions? Are they powered by hydrothermal vents at the seafloor, like those in Earth's oceans that teem with life? Or are they fueled by some other unknown process? Enceladus is small, barely 500 kilometers across, yet it has become one of the most promising places to search for life beyond Earth. Its plumes offer direct samples of its hidden sea. But until we return with new missions, the mystery of what moves beneath its ice remains unsolved. Titan has seas of methane, and something keeps replenishing them. Titan, Saturn's largest moon, is a world both familiar and alien. It has lakes and seas, rivers and rain, but instead of water, they are made of liquid methane and ethane. Titan's skies are hazy, its surface shaped by weather utterly unlike Earth's. Here's the mystery. Methane in Titan's atmosphere should be destroyed by sunlight over time. If so, the methane seas should have vanished long ago, yet they remain. Something underground or hidden in Titan's chemistry keeps replenishing them. Some suggest cryovolcanoes release methane from Titan's interior. Others imagine chemical processes we do not yet understand. Intriguingly, some researchers note methane can also be a potential biosignature, a sign of life. Could Titan's methane be biological in origin? We don't know. Titan's methane cycle mirrors Earth's water cycle in eerie ways. But the source that sustains it, the hidden pump that keeps its seas full, remains a mystery waiting to be solved. Mars once had flowing rivers, but we don't know where the water went. Billions of years ago, Mars was a very different world. Vast river valleys carved its surface. Deltas and lake beds mark where water once pooled. The planet may even have had oceans. Today, it is dry and frozen, with only thin traces of water vapor in the air. What happened to all that water? Some may be locked as ice beneath the surface. Some may be trapped in minerals. Much of it may have escaped into space when Mars lost its protective magnetic field. But the full story is unclear. Mars is covered in evidence of a wetter past, yet its present is a desert. Did the water vanish slowly or in sudden shifts? Could liquid water still flow underground today, hidden from our view? The fate of Mars's rivers remains one of the greatest planetary mysteries. To solve it may be to understand whether Mars once supported life and whether it still could. Mathematics describes the universe with uncanny accuracy, but we don't know why. Mathematics is a language of patterns, a human invention built from numbers, symbols, and logic. Yet astonishingly, it describes the universe with near-perfect precision. Equations imagined on paper end up governing stars, atoms, and galaxies. Einstein's equations predicted black holes before anyone had seen one. Maxwell's formulas described radio waves long before they were detected. Why should abstract symbols map so exactly onto reality? Some scientists argue math is discovered, not invented, and it reveals truths woven into the cosmos. Others suggest math is a tool shaped by the human mind, refined to fit the patterns we observe. But neither view fully explains the eerie effectiveness of mathematics in physics. Why should the same formulas describe both the arc of a thrown ball and the motion of distant planets? Mathematics is both a human creation and a universal key. Why it works so uncannily well remains one of existence's deepest mysteries. The constants of nature seem fixed, yet their values remain unexplained. Every law of physics depends on constants: the speed of light, the charge of an electron, the strength of gravity. These numbers define how the universe behaves. Change them slightly, and stars might never form. Chemistry might fail. Life could become impossible. But why do they have the values they do? Scientists measure these constants with exquisite precision, yet no theory tells us why they are what they are. Some suggest they are accidents of our universe. Others imagine a multiverse with countless universes holding different values, and we simply live in one where life can exist. But these remain speculations. The constants of nature are like settings on a cosmic dial, fixed, precise, and unexplained. They are the background music of the universe, a melody we can hear but not compose. We don't know if true randomness actually exists. Flip a coin, roll dice, shuffle cards. Randomness seems obvious. Yet physics makes the question stranger. At the quantum level, particles act unpredictably. An electron may appear here or there. A radioactive atom may decay now or later, with no cause we can see. Is this genuine randomness or just complexity beyond our understanding? Einstein famously rejected the idea, insisting that hidden laws must govern quantum events. But decades of experiments suggest otherwise. Quantum mechanics may be irreducibly random. Still, some scientists believe deeper rules remain to be found. Others think randomness is woven into reality's very fabric. If true randomness exists, then uncertainty is not just ignorance. It is part of what reality is. Whether the universe is fundamentally ordered or truly random remains an unanswered question at the heart of physics. Time itself is still one of science's greatest mysteries. We live in time. We feel it move second by second, carrying us from past to future. Yet science cannot fully explain what time is. Einstein showed time is not absolute. It bends and stretches with speed and gravity. A clock on a mountain ticks faster than one at sea level. A clock in orbit ticks differently than one on Earth. Time is woven with space into a single fabric. But why do we experience it as a one-way arrow? Why does the past feel fixed while the future stays open? Some physicists tie the arrow of time to entropy, the tendency of disorder to increase. But that only pushes the question back. Why was the universe born in such an ordered state? Others suggest time may be an illusion, a trick of perception. Time governs every heartbeat, every thought, every life. Yet its true nature remains one of the most profound mysteries we face. Matter exists, but antimatter nearly vanished, and we don't know why. When the universe began, the Big Bang should have produced equal amounts of matter and antimatter. But when matter and antimatter meet, they annihilate into pure energy. If they had been perfectly balanced, everything should have disappeared in an instant, leaving no stars, no planets, no people. And yet, here we are. Somehow, matter won. Why did matter gain the upper hand? Experiments show matter and antimatter behave almost identically, but with tiny asymmetries. These slight differences may have tilted the balance early on, yet they do not seem large enough to explain why anything exists at all. Somewhere in the physics of the early cosmos lies the reason there is something instead of nothing. Until we find it, the victory of matter over antimatter remains an unsolved riddle. Particles have mass, but we still don't know what truly gives it to them. Everything around us has mass, from stars to sand to our own bodies. But why do particles have mass at all? For decades, this was one of physics' biggest mysteries. The discovery of the Higgs boson in 2012 confirmed an invisible field that fills the universe. As particles move through it, they gain mass, like swimmers pushing through water. Without this field, matter as we know it could not exist. But the Higgs mechanism answers only part of the question. Why does the Higgs field exist at all? Why does it have the strength it does? And why do different particles couple to it so differently? The Higgs discovery opened the door, but behind it lies a deeper mystery. Mass feels solid and obvious, yet its origins remain partly hidden in invisible fields of the cosmos. Reality may be continuous, or it may be pixelated, and no one knows. To our eyes, reality looks smooth. Space seems infinitely divisible, like a line you can cut forever. But at the smallest scales, physics may behave differently. Some theories suggest the universe is pixelated, built from tiny indivisible units, like pixels on a screen. This smallest length, the Planck scale, is far beyond what we can observe, yet it might be the foundation of everything. If reality is pixelated, then space and time are not smooth, but granular. The rules of physics would need rewriting, but so far no experiment has confirmed this. Whether the universe is continuous or digital remains one of science's strangest questions. The answer could reveal the true texture of reality itself. There may be a smallest possible length of space, but we haven't found it. Physics pushes us toward ever smaller scales. Atoms, once thought indivisible, were split into protons and electrons. Protons themselves turned out to be made of quarks. Yet at some point there may be a smallest length, a boundary beyond which smaller has no meaning. This is thought to be the Planck length, unimaginably tiny, about 100 billion times smaller than a proton. At that scale, space may no longer be smooth, but foamy and uncertain, a quantum haze. But no experiment can reach it yet. If space has a smallest unit, then the universe is not infinitely divisible. Reality would have a bottom floor, the smallest brick of existence. Whether such a limit exists remains one of the deepest mysteries of physics. The laws of physics could have been different, but no one knows why they are what they are. The universe runs on laws, gravity, electromagnetism, quantum mechanics. They are elegant, precise, and consistent, but they might have been otherwise. Why this set of laws and not another? Why a universe where stars can form instead of one where matter collapses or drifts apart. Some scientists imagine countless universes, each with different laws, and ours is simply one where conditions permit life. Others think deeper principles, still unknown, lock the laws into place. But for now, the origin of the laws themselves remains unexplained. We can describe the rules. We cannot yet explain why these rules and not others are written into reality. And perhaps that is the greatest mystery of all. Whether we will ever truly understand any of this is uncertain. Science has carried us far. We have mapped galaxies, split atoms, decoded DNA, and walked on the moon. Each answer reveals more questions. Each discovery opens new mysteries. Perhaps one day we will explain consciousness, the origin of life, the birth of the universe, the nature of time itself. Or perhaps there will always be questions just beyond our reach, mysteries that cannot be solved because they are woven into the fabric of existence. The greatest mystery may not be the universe itself, but our place within it, whether human minds can ever truly comprehend the totality of reality. As you drift to sleep, you might hold that thought gently, that curiosity itself is part of the mystery. To wonder is to be human, and to seek is to be alive. The questions may never end, but neither will our search. You've just traveled through 100 of science's greatest mysteries, questions that stretch from the cells in our bodies to the edges of the universe itself. Each one is a reminder that for all we've discovered, the world remains far deeper, stranger, and more beautiful than we can fully grasp. Think of what we've touched tonight: the hidden spark of consciousness, the riddles of aging and memory, the secrets carried by oceans beneath icy moons, the timeless puzzles of stars, storms, and the fabric of reality itself. Some of these questions may be answered in your lifetime. Others may remain mysteries for generations, and still others may never be solved at all. But that is part of the wonder. To live in a universe that still holds so much unknown is to live in a universe filled with possibility. Every unanswered question is an open door. Every mystery is an invitation. The fact that we don't yet know keeps science alive, keeps curiosity burning, and keeps us leaning forward into tomorrow. And as you lie here now, letting the weight of these mysteries drift across your mind, notice how gently they pull you toward rest. Like the slow rhythm of waves on a shore, the questions themselves are soothing. They don't need answers tonight. They only need to be carried like starlight across a dark sky. So let your breathing fall into rhythm. Let your body grow heavy and your thoughts soften. Imagine yourself floating through the mysteries we've explored, passing by them as if through constellations in the night. Questions above, questions below, a galaxy of wonder all around you, and you at the quiet center, resting in the knowledge that mystery is not something to fear, but something to embrace. If you happen to still be awake, you can go ahead and watch the next video when you are ready. But for now, there's nothing left to do. No answers to chase, no puzzles to solve, just the calm certainty that mystery itself is a kind of lullaby, one that will carry you into sleep. Good night, and may your dreams be filled with wonder.